Hey, welcome back to Electrically Constructed. I'm Master Electrician Seth Eckel, and this is our 7th video in our Raceway Calculation series. In our last video, we covered Table 310.16. That was our introduction to the ampacity of insulated conductors. In this video, we are going to be going over Table 310.15C1. This is adjustment factor for 4 or more current carrying conductors in a raceway. If you are running wires in a raceway, you're going to really want to tune in and learn how to do this, because this is very important. If you don't get this, you're probably going to end up making a lot of critical mistakes when you pull wire in your raceway in the field. So pull out your 2026 NEC Code Book and let's get going. All right, guys, let's open up our code books to Table 310.16. So this is the table that we went over in the last video. This is the starting ampacity of our conductors. And this one has rules that apply to it. And one of those rules that apply to this table is for no more than 3 current carrying conductors in a raceway. So today we're going to go over Table 310.15C1. So let's go to that page. That's should be the page right before this one. And Table 310.15C1, this is the adjustment factors for more than 3 current carrying conductors. All right, so Table 310.15C1 generally comes into play when we have more than 3 current carrying conductors installed in the same raceway or cable. The rule can also apply to single conductors or multi-conductor cables installed outside of a raceway when they are all grouped together and they don't maintain the spacing that they need for more than 24 inches. But in this video, we're just going to focus on mainly conductors installed inside of a raceway. So before we start using this adjustment table, we have to correctly determine how many current carrying conductors are in the table. We don't want to just start counting every wire that's in the raceway. We want to make sure that we count only current carrying conductors. All right. So equipment grounding conductors are not counted as current carrying conductors. Neutral conductors, they must be evaluated under 310.15E. Some neutrals are counted and some neutrals are not counted. The code tells us how to determine that, and we're going to go over that in another video. We're going to actually go over that in the next video. We're going to figure out how to determine which neutrals count in our raceway fill and which neutrals do not. But in this video, we're just going to focus on how to understand and how to apply this table with current carrying conductors. All right. We also have to count spare conductors. They're usually counted in our raceway fill. And also if you have like travelers, you're only going to count one of those. Just want to make sure you guys understand current carrying conductors are what we count in raceway fill. But like a traveler, you only have to count one of them because only one of it's going to be energized at a time. What else? Oh, parallel runs, you're keeping those separated. You're not going to count the wires in one run and the wires in another run and combine them. You're going to keep those raceways separate. So all those things are things we got to think about while we're doing our raceway fill. So once we know how many current carrying conductors we have in our raceway, then we can use 310.15C to do our adjustment correction. So we have our number of conductors in the raceway on the left-hand side, and then we have our correction percentage on the right-hand side. So if we have 4 through 6 conductors that are current carried in our raceway, we have to correct our ampacity by 80%, and so on. So 7 to 9, 70%, 10 to 20, 50%. And that's a big jump. If you think about it, you go from 7 to 9 current carrying conductors for 70%. If you have one more conductor, 10 current carrying conductors in that raceway, you're dropping 20%. That's quite a bit for just one extra conductor in your raceway. So that's always something to think about when you're pulling a wire through. All right. Let's see here. Let's take a look at some slides that I put together to help explain some of these things we're talking about here. All right. So why conductor count matters. Every current carrying conductor produces heat. When we put more conductors together inside the same raceway or cable, it becomes harder for that heat to escape. The code accounts for that by requiring us to adjust the conductor's allowable ampacity. So you can see here, 3 current carrying conductors on the left side and 10 current carrying conductors on the right side. It's much hotter inside the raceway with more current carrying conductors. More heat, more resistance. More resistance, less ampacity. So that's why we have to correct the ampacity for these wires as they get heat up inside the raceway. Let's take a look at our next slide. In this one, we are talking about how to count our conductors correctly. So we got to make sure that we count only the current carrying conductors. We must correctly determine how many current carrying conductors we actually have. We need to evaluate the neutrals. We need to use 31015E, and we are going to go over that one in the next video. All right, but we don't want to assume that not every neutral counts, and we don't want to assume that not every neutral is excluded. We need to evaluate the neutrals by the code rule. All right, so we're going to go over that one a little in depth in the next video. All right, in 31015C1, key points. And I'm going to have all these slides again available for you on my channel in the post. So you can go there and get these. But these are the key points of this video and the rules and how to apply the rules to this table. All right, so it's 3 current carrying conductors, or more than 3 current carrying conductors. 2, applies to raceways or cables. 3, you got to get the total count of your current carrying conductors. 4, neutrals must be evaluated. And 5, parallel conductors count individually. All right, so these slides will be available on my channel. You can reference them as you'd like. They'll be under post. You can screenshot them, keep them for yourself, whatever you want to do with them. All right, next slide. Okay, so this next slide is teaching us the steps to calculating 31015C1. All right, so first you want to identify the conductor. In this example, it's THHN. So let's go over to our code book real quick and look at what I'm talking about here. So THHN is under the 90° C column. So that way I can use all the ampacities. These would be my starting ampacities for all the conductors in the 75° C column. You'd have to use this as your starting ampacity, and the conductors under the 60° C column, you'd have to use these as your starting ampacities. All right, same thing on the aluminum side. Look for your conductor type, insulation, and then you'd have to use that for your starting ampacity. Something I'm going to point out real quickly. Don't want to get too deep into it, but I want to just point it out. We're going to talk about it more in other series. But typically, when it comes to terminating conductors to equipment, we're going to use the 60° C column, 100 amps and less. So if there is like receptacles, switches, whatever equipment you're terminating to 100 amps or less, you're going to use the 60° C column for your maximum ampacity that you're terminating to. That doesn't change that our starting ampacity for adjustment is always going to be based on the insulation type and the highest degree temperature of that insulation type. All right, so we'll talk about that more. But if it's 100 amps, you're probably going to terminate to 60° C column. If it's over 100 amps, you're probably terminating to a 75° C column. At least those are pretty standard, typical rules that we go by. You can always change that depending if the stamp on the equipment that you're terminating to says something else. So if you are terminating to something that says 75, terminating to something that says 90° C, then you can use those ampacities for that kind of stuff. But I don't want to get too deep into that. Just wanted to touch on it a little bit. Next, step 2, use table 316. You know your insulation type. You pick out your maximum ampacity that you can start with, and then you count up your conductors, and then you go to table 31015 C1 to know what your adjustment factor is going to be. If you have 4 to 6, 80%, 70%, 7 to 9, 10 to 20, 50%, 45%, 40, and 35%. All right, and then finally you have your allowable ampacity. Once you know that, you take your starting ampacity times your adjustment factor, and you get your adjustment ampacity. Final ampacity cannot exceed the termination limits. That's what I was just kind of touching on a second ago. And it can't exceed other code rules that are going to apply that we're going to go over as well. Do not automatically start with the 60° or 75° C column. Use the conductor's 90° C ampacity for adjustment calculations, but only if the installation is rated for it. Then verify the final results against terminations and other rules. All right. Hopefully all this makes sense so far. And we're going to go over a few examples real quick. Why don't you keep your code book open and go through these examples with me through your code book as I talk through them on the slides. All right, example number 1. We got 6 12-gauge copper THHN conductors, current carrying conductors. We're going to start with ampacity. So number 12 copper THHN, 90°. Following along in your code book, you'll see that it is 30 amps. We have 6 current carrying conductors. If you go to your other table, 31015C1, you'll see that 6 current carrying conductors. The adjustment factor is 80%. You're going to take 30 amps times 0.8, and that's going to give us 24 amps. So our adjustment ampacity is 24 amps. So that means we can still use a 20 amp circuit. All right, let's do another example. Keep your code book out and try to follow along. This one is 9 12-gauge copper THHN current carrying conductors. Again, we're going to start with our ampacity. Table 31016, 12-gauge copper THHN. It's good for 90° C at 30 amps. We got 9 current carrying conductors. So the adjustment factor for 9 current carrying conductors in table 31015C1 is 70%. 30 times 0.7 is going to give us 21 amps. So once again, we're still good for a 20 amp circuit with those 12-gauge wires. All right, let's do one final example here. All right, now we got 10 12-gauge copper THN conductors, current carrying conductors. So we already know that we're good for 30 amps. We got 10, so we go to 31015 C1. Our adjustment factor is 50%. We have to take 30 times 0.5, and that's going to give us 15 amps. Result, 15 amps is not enough for a 20 amp circuit anymore. If we want to use a 20 amp circuit, we're going to have to go up to a 10-gauge wire, and that would be for 40 amps times 0.5, and that'll give us 20 amps. So something to think about when you're running wires. This is very high level stuff. This is what separates the foreman from the guys that are just installing. The foremen are looking at this ahead of time, knowing what kind of conductors they want to pull through their raceway, knowing that they want to run a 20 amp circuit. They want to pull 10 current carrying conductors through that raceway. They're going to have to run number 10 gauge copper wire so that they can run that 20 amp circuit. We are going to definitely do a lot of these examples on our Bluebeam blueprint layouts, and we're going to run a bunch of different scenarios. So that's going to be in a few videos from now, but we're definitely going to play with a bunch of different scenarios with this. All right, so hopefully this all made sense. In the next video, we're going to go over the neutral conductor and how to determine if a neutral conductor is counted as a current carrying conductor or if it is not counted as a current carrying conductor. All right, but that's all I got for you in this video. So can't wait to see you in the next one. Stay sharp, never stop learning, and God bless.